Hello, everybody. Welcome to session 5 of module 3 of the subject Water Supply and Treatment Engineering, 18 CV 46 for 4th semester civil engineering students. This program is this program LMS is initiated by Department of Collegiate and Technical Education, Government of Karnataka. See, in the session 4, just to recall what we have discussed is we discussed about coagulation, sedimentation aided with coagulation. I'll repeat. In the sedimentation process, we are going to remove very fine suspended particles which are easily settled in the tank using the force of gravity. There are some particles which are very fine, very small, which does not remove even after giving a large or enough detention time. So for those particles, what we do is we add chemicals to the sedimentation tank wherein these coagulants are going to have chemical reactions and makes flock formation, and these flocks are going to attract the very fine particles and settle down. This is what happens in the coagulants coagulation. And we have discussed even at the end of the session 4, we have discussed about what are the different types of coagulants which are generally used. Alum and iron salts are generally used, and alum has got its own advantage and iron has got its own advantage. In the session 5, we are going to find out how much or what is the dose of coagulant that can be added to the water, and how do they estimate all the dosage of coagulants. We'll understand, we'll find out, and we'll try to know that. And in the contents, we are also going to understand what exactly is sedimentation coagulation tank, how it is different from plain sedimentation tank. This one thing we will discuss. And at the end of the session, we are going to discuss about jar test also. What exactly jar test, what do they do? I'm going to let you know all these things. Let us take a problem. I have pasted a problem. The problem is determine the quantity of alum. Alum is a coagulant. Its chemical formula is aluminum sulfate Al2SO4 thrice 18H2. Determine the quantity of alum required in order to treat 13 million liters of water per day at a treatment plant where 12 ppm of alum dose is required. Also determine the amount of carbon dioxide gas which will be released per liter of water treated. So this is the question. See, they have given the amount of water treated in the treatment plant. It is given 13 million, that is 13 into 10 to the power of 6 liters per day. For 24 hours, they are going to treat this amount of water. What is the alum dose they have found? They are adding 12 ppm is nothing but milligram per liter. 12 milligram per liter. For every 1 liter of water, they add 12 milligrams. So the question is determine the amount of carbon dioxide produced and per liter of water. This is what they have asked. See, what is the amount of alum required per day? For every one dose, we add 12 milligrams. In a day, we treat 13 million liters. So 13 million liters into 12 milligram gives you so much of milligrams of water. It is been converted. Finally, it comes as 156 kg of alum is required in the treatment plant for a day. For a day, they require 156. Another part of the question is we have to find out what is the amount of carbon dioxide that is produced. To find out that, you have to write down the chemical reaction. So when alum is added to the water, what will happen? Al2SO4 thrice 18H2O, when added to water, the natural alkalinity which is present in the water as bicarbonate alkalinity, which is CaHCO3 twice, gives rise to aluminum hydroxide, that is 2AlOH thrice, which is down direction, which is precipitate, plus calcium sulfate plus 18H2O plus 6CO2, which is carbon dioxide. This is a balanced chemical reaction. If you check the molecular weight of the alum, that is aluminum 2, 2 into 26.97, 3 into 32.066. So if you compute the molecular weight of the alum, it is 666. Molecular weight of carbon dioxide is 44. Means, that means, see, uh, 666 milligram of alum is used will release 44 milligram of carbon dioxide, because molecular weight of this one part of aluminum sulfate, understand, 666 produces 44 milligram of carbon dioxide. Okay, it means that 666 milligram of alum if used will release 6 into 44. 6 into 44 is the amount of carbon dioxide present in the water. So the question is, what is the amount of carbon dioxide which will be released per liter of water treated? For every 1 liter of water, what is the amount? For 666 milligram, we get 6 into 44 milligrams of carbon dioxide. So what is for 12 milligrams? That is 6 into 44 divided by 666 into 12. You get 4.76 milligram of milligram of carbon dioxide is released. So since till 12 milligrams of alum is required for treating 1 liter of water, the quantity of carbon dioxide released or evolved per liter of water is 4.706. Again, I'll explain. See, chemical reaction you have to write down, that is known. One part of aluminum sulfate produce 6 part of carbon dioxide. So one part of aluminum sulfate molecular weight 66, 6 part of carbon dioxide is 44. 6 part means 6 into 44, that is one part of aluminum sulfate produces 6 part of carbon dioxide. What is 12 milligrams of alum produces, or 12 parts? Nothing but 6 into 44 divided by 666 into 12, which is 4.6 milligrams oxygen for every 1 liter of water. So that is what the answer is. This is as far as aluminum sulfate is concerned. Well, let us see another problem. Problem. Problem is this: 8 milligrams of copras. Copras, you know, is an iron salt, ferrous sulfate, is consumed with live at a coagulation basin per liter. Determine the quantity of copras and the quicklime required to treat 10 million liters of water. So, what is the dosage of copras is required? And for every time when we add copras, it needs natural alkalinity. If it is not present, we have to add lime also. So, what is the amount of lime that is required? Quantity of copras required per liter of water is 8 milligrams. That is what is consumed or we added. So, what is the quantity of copras required for 10 million liters? See, for every 1 liter, we have to add 8 milligrams. For 10 million liters, we have to add 80 kg. It is converted to milligrams to kg. Now, the question is, when quicklime is added to the water, it forms calcium hydroxide or hydrated lime. CaO plus H2O gives you CaOH twice. And copras is added, FeSO4 7H2O reacts with calcium hydroxide, CaOH twice, gives you ferric hydroxide, calcium sulfate, and 7H2O. This is the equation you get. See, to react, copperas requires, excuse me, copperas requires lime, alkalinity always to form ferric hydroxide. Ferric hydroxide is the precipitate which attracts the small particles. So, to form ferric hydroxide, there should be enough alkalinity. Alkalinity is not there, we have to add externally. So here we have added calcium hydroxide to the water. It forms calcium hydroxide, and copper is added to that. It reacts with hydrated lime or calcium hydroxide to form this equation: ferric hydroxide CaSO4 plus 7 Now let us see what is the molecular weight of the copper as. It comes as 278. What is the molecular weight of quicklime? It is 56 CaO. Ca is 40 plus 16. It is 56. That means for every one part of copperas, 278, we require 56 milligrams of quicklime. So 278 milligrams of copperas requires 56 milligram of quicklime to form ferric hydroxide. So what is 1 milligram of copperas needed? 1 milligram of copperas needs 56 by 278 milligram of quicklime. So 1 milligram of copperas needs this. What is our question? What is the amount of lime required for a day? For a day, we use 80 kilograms of copperas. So 56 divided by 278 into 80 kg is 16.12 kg of quick lime required. So quantity of lime required is 16.12 kilo. So again I'll explain. 8 milligrams of copperas is added to the water, or iron salt is added to the water as a coagulant for 1 liter. For 10 million liters, how much you have to add? 10 million liters into 8. It is converted into milligrams, converted into kgs. So when that copperas is added, it reacts with calcium hydroxide. So in this question, they are saying it is not in the water. So we have added externally quick lime. They have brought the quick lime from the market. What is the amount of lime that has to be added? So CaO plus H2O gives CaOH twice. FeSO4 7H2O CaOH twice gives you ferric hydroxide. So 278 milligrams of copperas requires 1 milligram 56 milligram of quick lime. So 80 kg of copperas is 56 divided by 278 into 80 gives you 16.12 kg of quick lime, which is needed. So these types of question may be asked in the examination. So this is as far as finding out the dosage of coagulants required. Let us study. See, I've been telling you it's a coagulation sedimentation tank in the slides. What exactly is the coagulation sedimentation tank? See, it's this sedimentation tank only. We have some additional devices with this. So the coagulation sedimentation plant, sometimes called simply coagulation plant, or a clariflocculator, which contains following four units: feeding devices, mixing devices, flocculation tank, and sedimentation tank. Feeding devices, what is this? Feeding device is nothing but the coagulant you are going to add through that feeding devices. So there will be by a mixing channel, and here you are seeing the figure. We add coagulants through these feeding devices. There are two types: dry feeding, or it is also called as wet feeding. You can feed directly, dry feed, or wet feed. So here also it can be mixed like this. And coming to the mixing devices, see, when the coagulant is added through the device, and it has to be mixed properly. Mixing can be done using mechanical mixer, or it can be used using flow. So if you take the flow in the left, right direction, and the vertical flow, the water is going to mix up with the coagulant. In the horizontally, you can provide baffle valves. There also you can have a mixing device. Mixing the flow will be, the water will be mixed with the coagulants, or you can use this baffle tank, or you can use mixers. mechanical mixers. So these are all baffles. The inlet is there and walls are there. When it is going to take turn left, left, right, left, right, left, right, the coagulants are going to mixed with the water. So this is the round and end type. Second one is over and under type of mixing. Horizontally baffle tank, the water flows horizontally. The baffle walls help to create turbulence and thus facilitate mixing. Mix more like we have to create turbulence that is caused by. So if you provide a wall, it is going to splash the wall, mix up very easily and turns. So turbulence is created, then mixing takes place. With the help of vertical baffle tanks walls also definitely turbulence can be created and facilitates mixing. So here you can see the baffle walls. So when the water enters, it moves right, left, right, left. So turbulence is created, and it is going to mix up, or the coagulant is going to mix up easily. Here you can see the baffles here, walls. ಸಡನ್ ಆಗಿ ಹಾಗೆ ಫ್ಲೋ ಮಾಡಕ್ ಬಿಡಲ್ಲ ಸೊ ಇಟ್ ಮೂವ್ ಲೆಫ್ಟ್ ರೈಟ್ ಸೊ ಟರ್ಬುಲೆನ್ಸ್ ಕ್ರಿಯೇಟ್ ಮಾಡಲಿಕ್ಕೆ ಈ ಥರ ಮಾಡ್ತಾರೆ ದೀಸ್ ಆರ್ ಆಲ್ ಮಿಕ್ಸಿಂಗ್ ಡಿವೈಸಸ್ ಆರ್ ಯು ಕ್ಯಾನ್ ಯೂಸ್ ದಿಸ್ ಒನ್ ಆಲ್ಸೋ mixer, sorry, after this one, flash mixer. So flash mixer, it runs through some motor arrangement, electrical motor. It is going to mix up the coagulant and the water. Okay, then it is taken to the next process. So first is the feeding device, next the mixing device. So mixing device may be using baffled walls, vertical or horizontal walls, or a flash mixer. Next, third portion is flocculator. See, in the mixing, flash mixers runs with high speed. It is going to mix up. It agitates very well. Once it is done, it is next taken to a flocculating chamber where again the water is mixed very slowly with the help of these flocculators for some time. That's called. It may the flocculators may be a horizontal flocculator or a vertical type of flocculator where the motor runs very slowly. Here I can show you this. This is a flocculating chamber. First is the inlet, then the mixer, then the flocculator. Here to form flocks. If you turn the water or if you mix the coagulants slowly, it will form a very good gelatinous flocculant material. So this happens in the flocculating chamber. Here you can see horizontal shaft flocculator or vertical or this type. And here also you can see flocculating chamber. It is going to these using motor arrangement. They'll mix the water slowly. Flocculating chamber motor runs very slow with a very slow pace. Then it is taken to the settling chamber. These are the constituents of coagulation sedimentation tank. Now we will move on to the jar test, generally done in the laboratory. What is the jar test? Jar test is a laboratory procedure to determine the optimum pH and optimum coagulant dosage. See, most of the dosage depends upon the pH of the water also. So a jar test simulates the coagulation and flocculation process. How do they determine the optimum pH? Take some jars, fill the jars with raw water. The raw water that is to be treated, 500 to 1000 ml, usually 6 jars. Adjust the pH of the jars while mixing using sulfuric acid or sodium hydroxide depending upon the pH. 5, 5.56, 6.577. Natural water temperature, the pH usually ranges from some 5.5 to 8. So we have in this one they have taken 3 plus 3 6. pH. So add some dose of selected coagulant, maybe alum or iron, to each jar. Maybe 5 to 10 milligrams per liter of this one is added. So if you take 1 liter jar, add 10 milligram or 5 milligram. Then rapidly mix. Initially, you say flash mixer, as shown in the previous slide. So first it has to be flash mix. Agitation should be very high. After that one, in the flocculating chamber, generally in the treatment units, we run the flocculating chamber very slowly. So here also what we do, we reduce the speed of the flash mixer. Then we gently mix with a RPM of 25 to 30 RPM. And afterwards, we have to take it to flock formation will takes place. Okay, then allow the flocks to settle down, which happens in the sedimentation tanks. So turn off the mixers and allow the flocks to settle 30 to 45 minutes time. So whatever which is present in the jar, they are going to settle down. Afterwards, take out the supernatant or the top water and test the pH. Then plot the graph like this. So at 5.5, you may get turbidity of 10 NTU, 5.5 this one. So lowest turbidity, whatever you are going to get, find out the pH of that one. That is the optimum pH in between in this experiment 6 to 6.5. Once the optimum pH is found using the jar test, next is the dosage test. What is the optimum dosage? See, just we cannot random add 5 milligrams, 6 milligrams, 7 milligrams. We have to find out the optimum dosage so that we can avoid cost escalation in the maintenance of the treatment units. So repeat all the previous steps. Take 6 jars, add the water, understand? Then adjust the pH of the water to 6.3, because we have found in the previous slide 6.3 is the optimum one. So 6.3 is maintained in all the 6 jars. Now we are going to add alum or iron in different dosages: 5 milligrams, 7, 10, 12, 15, 20 milligrams. So when the coagulant is added, first thing is in the mix. First is the mixing device. That means we are adding the coagulant here in this case through our hands only. Then mixing rapid mixing for 1 minute at a speed of 100 to 150 rpm. Then the third step, as it takes place in the flocculating chamber, slowly you're going to stir it for 15 to 20 minutes at a speed of 25 to 30 rpm. Then leave it for some time, 30 to 45 minutes. All the flocks which are formed will settle down. Plot the graph. You're going to plot the graph turbidity versus alum dosage. So you have added the 5, 6, 10, 12, 15, this one. You got the points. Plot the graph. Okay. So at 12 milligrams, 12 point something milligrams of alum dosage, you have got the minimum turbidity. Means most of the particles have been suspended, have been removed, have been settled down. So that is the optimum alum dosage or iron dosage. In this case, it is um, around 12 point something. This is how optimum coagulant dosage is calculated. So these are the references. Thank you.